It's going to be a little bit of delay before we figure out slides. But like, if you happen to have questions, like, I'll be happy to take like questions from like the first half. Slides are up. Could I just go then, or? Okay. So welcome back to the second half of the talk, where I talk about topic of the talk is on data structures and optimization, and this half of the talk is going to be focusing on graphs. So first of all, why? I mean, so recall from before that max flow, the way you solve it is you just repeatedly do pathfinding, where you flip edges around. Why do we have to take a detour through optimization? And here, in my personal opinion, it's very much a question of how big of a difference do you believe there is between directed and undirected data structures? I went to, like, when I started thinking about these things, was at a point where there was huge differences between, say, like the undirected and directed reachability. My understanding is that like some of these differences are not as pronounced as like basically like at about like 2014, 2015-ish. So I think a lot of the rationale is not very generically applicable. So let me just say why this route kind of makes sense. And the key idea is that there was this result by Deitch and Spielman that kind of was the first one to apply interior point methods to the network flow problem. And the most kind of interesting thing there is that the residual networks are undirected. And as a kind of more of a user to dynamic graph data structures, it was just kind of natural to kind of stay in the undirected setting because there is like there are just more tools that were available. So just a quick refresher, dynamic graph data structures. The idea is that I have a graph where the edge weights are continuously changing, and I want to be able to recompute answers faster than recomputing from scratch. So the problem is that like dynamic linear system solving, or more generically, dynamic optimization on a graph, this is a problem that at least lets you solve dynamic reachability, like even an undirected graph. So kind of the one thing that's kind of often, like one thing that kind of makes this kind of a very daunting starting point is just how tricky the dynamic connectivity data structures are, even for undirected graphs. So kind of the approach that were taken was essentially to kind of take ideas that were already developed for dynamic connectivity and try to emulate some of them on, but still on undirected graph, but with some of these kind of optimization objectives in mind. So there were two tools that somehow just were like, basically there were two tools that were, so the kind of the natural starting point is with interior point is you have systems of linear equations. On graphs, these are specialized matrices known as graph Laplacian matrices. And kind of the way that kind of some of this work started was that there were kind of just like direct analogs between things in the dynamic connectivity literature and the Laplacian solving literature. So the Laplacian solving literature is what was kind of inside the Deitch-Spielman max flow algorithm. And dynamic connectivity, so this is kind of like the quintessential dynamic graph data structure. In particular, there are two pieces that are very much in common. One is called edge sparsification. So edge sparsification actually was kind of the hardest piece in the kind of the Laplacian solving literature. And in fact, it was actually first introduced, the term was actually introduced in a paper that was titled Sparsification, an approach for speeding up dynamic graph data structures by Epstein, Galileo, Italiano, and Nissenwig. The other one that was not formalized until very recently, but has kind of very direct connections, is the ability to remove vertices. Removing vertices for linear system solving, that's Gaussian elimination. And we'll get to that in a bit. But removing vertices, what is that for dynamic trees? That's basically rake and compress. So that's the ability to get rid of leaves, and that's also the ability to compress path. So somehow you can view basically a lot of these data structures, especially the ones, so things like top trees, as essentially some kind of local elimination rule applied in like log and levels. So with this in mind, the plan is I'll try to talk through how both of these were kind of developed to be kind of more friendly to dynamic graph algorithms, and hopefully getting to the point where, it's kind of possible to get some intuition about like how some of these recent developments in network flows are working. One thing that is worth mentioning before I start diving into details is that the current style results have a very unsatisfying aspect to them, which is that they aren't like direct interaction between optimization algorithms and data structures. So the problem is that basically most of our current technology for, especially for getting high accuracy sparsification of graphs, a lot of that is randomized. So you get this into this issue, which is what Thatchable talked about, which is this adaptivity. So how to, the problem is that, I mean, the way to kind of describe, the simplest way I like to describe this phenomenon is that if I have a randomized data structure and I give it its own output, I give it input that depends on its output, now the input has dependence on its randomness. And the issue is that usually when you analyze these data structures, you assume some kind of very strong kind of independence between your coins and your input. So you get this kind of situation where the data structure are randomized, and the data structure affect your next step in optimization, and thus affects the input into your data structure. So actually, all the recent development they all had different ways of addressing this. This is the only place I will really talk through them. For the rest of it, I'll just talk through oblivious data structures, and then at some point there's kind of a need to suspend disbelief and just like pretend that like basically oblivious can be used. But just quickly, the initial thing that we did is in okay, so basically all the improvements over 1.5 for general capacity graph. So the sparsification one didn't have this issue. But the first one actually used the fact that the solutions generated by path-following algorithms are pseudo-deterministic. So there's this kind of a survey by Shafi Goldwasser on pseudo-deterministic algorithms, which are randomized algorithms that are guaranteed to always produce you the same output. And that was kind of a very natural kind of starting point for showing that like some of these randomized data structures can be made to work. Of course, as you look further into it, you get to adversaries. But then kind of in the more recent stuff, the data structures were actually, we realized that sometimes the oblivious is actually not so bad because the solutions that's actually being maintained, like the solutions that's kind of you're comparing against is actually stable. So they're stable enough that like the only things that are changing are on the edges that's being updated. Like you can basically prove that opt only changes a lot on things that are being updated. So this led to what's called this led to a whole definition called a hinted flow chasing and a rebuilding game, which is actually one of the kind of well, I was just telling Thatchable over the break that is actually kind of one of the most like fragile points in the kind of the most recent development. Like we spend a lot of time kind of line checking that. But so there's this whole kind of separate discussion about like there's like basically like all the data structures that's being used right now are randomized, and like I feel that basically generic kind of generic points on like what is this phenomenon, how to better understand it. And by the way, this phenomenon to me was always extremely frustrating because I like to work by experiments. So for example, like at some point I try to code the King-Kaplan-Mountjoy data structure because that one was defined for, so there's this like sketching-based dynamic connectivity data structure. I try to code it and I try to generate input where it's breaking and I just couldn't do it. So like I try to basically have a situation where like I like write an outer loop for it where like it actually breaks the data structure. I just couldn't do it. So it's kind of an exceedingly frustrating situation in that like I feel that like for this kind of situation where you're using randomized data structure, it would be nice to even have like concrete like outlines of, oh, like this is a bad outer loop for like here's a bad like non-trivial outer loop for this randomized data structure. I feel even that is missing right now. Any questions about that comment about like adaptive adversaries? Yes.
Yeah, so quick question. Isn't pseudo-deterministic just equivalent to adaptive adversary?
Oh,
what's the difference?
The difference is that the modification is happening on the outer loop. So the data structure is still oblivious adversary data structure, but you can modify your data structure, your outer optimization loop, to kind of like snap back to a central path point. So the modification is not happening in the data structure; it's happening kind of in the optimization algorithm. Other questions? Okay. So, okay, so hopefully I've kind of hidden the most kind of intricate issue under the rug at this point. But if you think there is like, I haven't done a sufficiently good job hiding it, maybe just please suspend disbelief for the next like 20 minutes, and then I'll be happy to talk more about it. How am I doing for time? Okay, well, next 15 minutes. Now I just want to talk about the two pieces. One is that graph sparsification. This is actually an extremely robust piece. Their results essentially from functional analysis that says for any matrix and any norm, you can do what's called row sampling. You can sample some rows of the matrix so that the resulting linear operator is well approximated. In kind of combinatorial terms, what this means is that you can, for any dense graph, undirected, you can generate a sparse one where you preserve all cuts, you preserve all eigenvalues, you preserve a lot of things. Let me try to quickly sketch out how I like to think about graph sparsification. I think of it as the multivariate version of Chernoff bound. So what does Chernoff bound say? Chernoff bound says that if I have a bunch of values, positive numbers, that each of which is less than, say, order log n of the sum, a random half of them get me roughly close to half the sum. Graph sparsification is the multi-dimensional version of this. There's what's called matrix Chernoff. So basically, everything that you know about Chernoff also holds for matrices. And kind of the good thing about like these graph objectives, because they're Hessians, they're actually positive semi-definite. Like they're second-order derivatives, so they're Hessians of convex functions. So they're positive semi-definite objects. So they're actually all positive in the operator sense. And in the operator sense, you also have this phenomenon, which is that if I have a bunch of matrices, each of which is less than, say, order log n of the sum, in the operator sense, random half of them preserves the sum up to a constant factor. Problem is that these are d-dimensional objects now. These are n-dimensional. Like these graph matrices on graph, they're n by n. So instead of having order log n for one-dimensional, that n just goes into the dimension of the problem. So you need order n log n of these to get a sparse approximation. And furthermore, there is this, like once you have this definition, which is you want to look for things that are less than the graph, you can also kind of derive that expanders are just nice. Like expanders basically contain, like all the edges that, like one sufficient condition for just tossing random coins, like fair coins on edges, is that you're sparsifying an expander. And the reason there is that the graph object, the operator, is actually just approximated by its degree. And so basically, if you have an edge, that edge is also less than just like 1, 1, or 2, 2 on the diagonal. So if the degree is bigger than order log n, you have a diagonal matrix, which is bigger than order log n, and you have like constant on the diagonal. As long as the degree is bigger than order log n, you have this condition, which is that the edge is less than the graph. Well, edge is less than the graph divided by log n. So basically what you can show is that as long as you have expanders where the degree is bigger than log n over, actually, I'm missing a phi squared there. I think it's some polynomial in the expansion. You can just show that you can go sample these graphs. And furthermore, there's been a lot of very beautiful work on maintaining expanders in dynamically changing graphs. So the idea is that you can also show that expanders are just extremely well-connected objects. And deleting, say, k edges from expanders, you only have to delete, say, order k things from the expander so that the thing still stays as an expander. So basically, expanders are also very robust to local changes. So you can get the dynamic sparsification algorithms that are basically just take all the edges that are changing, delete them from the expanders, reformulate, like just rebuild expanders on the things that were removed, and repeat. And this is actually a polylog per update kind of expander decomposition algorithm, well, dynamic expander maintenance algorithm. And once you have these expanders being maintained, what you can do now is at every step of your optimization algorithm, instead of looking at all the edges, you just go sample a sparse approximation and go solve the step problem on that sparse approximation. And what that gives is that, well, you also have to do something about like being able to detect weight changes. It turns out expansion is also friendly to looking for weight changes. In fact, what you can show is that these interior point methods are primal dual. So there's actually dual variables sitting on the vertices. And you have a weight change if and only if the vertices weights have changed. So you can just like go to your expander decomposition, dig them out that way. And then you can just like always work on sparse instances. So what this gives now is that instead of solving an order m-size linear system, you solve an order n-size linear system. Coupling this with the square root m iteration count, you're looking at n times n, which is n squared. And this was over the last couple of years, this was kind of the first indication that like there's something that's kind of very there's something that's very subtle about the ability to combine network flow, a interior point-based max flow algorithm, and a dynamic graph data structure. So sparsification is getting rid of edges. We also need to get rid of vertices. How do we get rid of vertices? For linear systems, there's a very natural solution, which is you just eliminate. Just do Gaussian elimination. You can show that Gaussian elimination exactly preserves the operator structure. I think part of the reason that we kind of went down this route was that there were just such a, eliminations in general are hard. And the reason is that if you eliminate on a graph, you quickly get dense graphs. So just like be able to eliminate some vertices and like directly produce a sparse approximation is already a fairly hard problem. This kind of started off in separable graphs. And actually, this was then later extended to general graphs. It turns out that eliminating on general graphs, what it amounts to simulating random walks. And through kind of better simulators of random walks and so on, one was able to get algorithms that were slightly sublinear. So the cost per update and query ends up being something like n to the 5/6. So the generic idea is you eliminate some vertices, then you throw the output into a sparsifier. So now you're working on a smaller subset of vertices, and you're working on a sparse graph on that. And that lets you basically take steps in sublinear time. So in general, on general graphs, this was basically, you just, for every edge, the routine ends up being that for every edge, you random walk it onto C. There's actually a whole bunch of ways of building this. There's actually extensive literature on how to simulate random walks on graphs. There's things like localization. There's a big literature on generating random spanning trees. This is all related in the sense that somehow eliminating on a graph-based linear system is somehow equivalent to just simulating random walks. There was like a lot of effort on this over the past 2 years. And actually recently, yesterday, there was a presentation that got to 1.5 minus 1/58 for runtime. So the issue there is like 1/58 is still a very small improvement. So then the question is like, do we really need to, like at some point one started asking, maybe we don't really need to be glued to L2 intermediate problems. And kind of the more recent stuff, kind of the starting motivation is what is friendly to elimination. And this is kind of where the connection between trees and vertex, like dynamic trees and vertex elimination really comes in. is that it turns out that the graph that's actually really easy for elimination are trees. You can show that if you have a graph and you have k key vertices, by just doing elimination of degree 1 and 2 vertices, you can get to an object whose size is order k. In fact, this is actually used a lot in the kind of the earlier works on solving graph structured linear systems. And there's also work on getting hierarchical routing schemes. So one reason we like hierarchical routing schemes is precisely because if you have k terminals, the problem becomes an order k-sized object. So this is like the earlier Spielman 10 work, and also the work by Reiki on building oblivious routing schemes. And it turns out that on graphs, there's actually a very kind of natural class of objects called J-trees that are essentially tree-like. So this was kind of first used to give almost linear time cut approximations, so being able to compute the mean cut between two vertices in almost linear time. There were subsequent work in distributed algorithms that really clarified what is the role of this. In fact, what that one said is that I actually don't need to generate kind of the full collection of like J-trees as in Madri's result. They just need to generate downsample the tree to something like order log n. So there does exist very efficient and locally updatable things for approximating cuts and distances, well, transshipment costs. So L infinity and L1 objects on graphs in almost linear time. And so the kind of the work kind of that went into this was that actually the initial projects were motivated by just the question of how well can we maintain a mean cut, like all pairs mean cut on a dynamically changing graph. And what we showed there is that this can be made dynamic by just like shortcutting some routing. So what you do is you, instead of doing a full routing on a tree, you just have some key terminals. You shortcut the routing at those terminals, so every edge kind of snaps to like two endpoints between tree endpoints, between two endpoints between like two key vertices on a tree. You take the tree, you do an elimination, so you're just left with the terminal vertices and like twice as many vertices, sparsify that graph, and you can build like kind of recursive data structure like this. And the kind of the more recent development was that this is actually friendly to second order methods. So once again, the kind of the trickiness here is that there's like being able to sample the tree count to order log n. There's actually a very kind of oblivious step that's going on here, and that also does not work for L2, which is why kind of the entire algorithmic structure has to work for L1 instead. So that's all I want to say about the interaction with interior point methods on dynamic graph data structures. I feel this is kind of one of the most like surprising kind of topics in graph algorithms, in that there's a lot of flexibility in designing optimization algorithms. There's a lot of flexibility in designing data structures. There's even a lot of flexibility in deciding how your data structure interacts with the optimization algorithm. As I have a little bit of time left, I actually want to talk about kind of problems here that's kind of more kind of static algorithm style that I feel would actually significantly simplify kind of the friendliness of a lot of these algorithms for dynamic settings. Part of the issue is that a lot of these tools, so spectral sparsification, J-trees, they were originally built as static. And they're actually, from the perspective coming from dynamic data structures, there's actually a whole bunch of things that's kind of undesirable. So for even graph sparsification itself, getting a determinist, so there's a question of like, could we just make all these things adaptive? And one of kind of the first bottleneck is that we don't even have a deterministic graph sparsification algorithm that gets error better than, say, the expansion. So the kind of the issue with interior point methods, L2 interior point methods are actually very fragile. So they actually want error that's kind of in like the 1 plus epsilon, or like where epsilon is something like 1 over polylog kind of regime. So the kind of one of the big issues there is actually that even if I have the expander decomposition, it's hard to dynamically maintain a good sparsifier on it. Like at some point, the way the current algorithms work is they actually go through every vertex, and that kind of like in kind of recursive scheme that immediately pays a number that is basically either a n or like some exponent of m. So like I feel that something like that is kind of necessary for like getting a proper like adaptive data structure to work with interior point methods. Some intermediate questions there is maybe I can get sparsifiers that preserve degree. Is it possible for me to do adaptive decremental without expanders? Like basically, like I feel like there's actually a lot of graph sparsification questions, even in static settings, that are not fully looked at. For dynamic sparsification, kind of going the other direction, is right now for dynamic sparsification, we're making combinatorial arguments. There are these things called matrix martingales, which are extremely powerful and give you near optimal bounds. Is it possible kind of we can kind of take like these kind of turn-off bounds and make them kind of more kind of friendly to dynamic algorithms? So here so actually in the incremental setting, this is no. But what happens if you have to say both increments and decrements? Is there still just some kind of matrix turn-off adaptations? And then finally, the thing that's really kind of, I feel is kind of the hardest problem like related to this topic is what is the proper way to eliminate vertices? So J-trees is kind of a very high error and like very kind of randomized kind of structure. Is it possible to just have something that's like, I have a graph, I have these terminals, could I just preserve this kind of structure? Like, could I just preserve, say, like all pair max flow structure between terminals or something like that? There's, like the existence of Gomory-Huchery and the existence of very good algorithm for Gomory-Huchery is very strong evidence that like something kind of, for this kind of more general definition should also work. But at the moment, they only work for C-edge connectivity, and the results are exceedingly messy right now. And exceedingly messy and also not complete. So with that, I will stop and be happy to take questions.